Okay. Next speaker is Professor Ki-Seok Kim from Postech. He will be give us talk about spontaneous chiral symmetry breaking with C equals to infinity in an emergent holographic dual description. Would you please start?
Thank you very much. I would like to thank organizers for giving me this nice opportunity. In particular, I appreciate Junggi's great effort for organizing this nice workshop. So today, I will discuss some vacuum solution in an emergent holographic dual description. Essentially, all relevant calculations have been performed with Yoon-Seok, not by me. Then let's start. So, as discussed in the previous talk, Sang-Bin-Sin's talk, so let me point out first about the strong coupling nature. So as far as I understand, a characteristic feature of the strong coupling nature is that physics is involved with whole electrons inside the firm surface. Suppose a certain lattice model. So let's consider some very simple lattice model. Some I and J means some site index, and I means site index, sigma means spin index. So usually we consider in this limit, so we are in this case we consider this term as a UV fixed point and dealing with this interaction as perturbation. But in this case, instead of involving whole electrons near the firm surface are main actors. However, if we consider opposite limit, you consider this term as a UV fixed point, then dealing with this term as a perturbation. So this intuition leads us to introduce a new expansion parameter, so-called dimension. So I will talk about more. So this system is basically already introduced before. Mode transition, quantum phase transitions in almost flat band system, and SYK models, blah, blah. Indeed, there is a description to mimic this kind of physics that is so-called dynamical mean field theory description. Basically, dynamical mean field theory description basically considering this interaction term as a UV fixed point, and you deal this kinetic energy as a perturbation. In this simple model, so interestingly, this when you're dealing with this perturbation, I introduce some parameter D. These dimensions, special dimension. It's like if we consider some QED coupling, like it's like if we consider some flavor, then it's like introducing lutein to match the flavor, some NF, some flavor number. So in this case, if we consider some perturbation, if you and leading second order cumulative expansion, you can consider IJ. Then see this sum, then factored out that in the leading order that gives dimension T. Then they are cancelled. Indeed, if you consider perturbation for the kinetic energy, you are allowed to consider 1 over T expansion. This is a new expansion parameter in strong coupling approach. And this will be further discussed in later talks in condensed matter section in this workshop. Basically, this is justified in the infinite dimension limit. Then the question is, but many things appear below infinite dimension, and 3 2, 3, or 4, whatever. The question whatever finite dimensions. This also reminds me of some pure holographic description, so-called extreme black hole. In the case of extreme black hole, we know that the dimension is effectively reduced. If we consider some Rn 85 black hole, then in the extremal limit at IR, you have 82 Rn black hole. This is so this is basically 0 plus 1D QFT. This is some holography. In this case, the main feature is the so-called dynamical critical exponent diverges. This is a one-strong coupling nature. So here the question is, can we derive this dynamic critical infinity fixed point at finite dimension in a natural way? Natural way means that suppose G equal 1 UV and G equal infinite IR, some RG flow. This is the question. Then, of course, this requires some infinite of the resummations for quantum fluctuations. So here, I will consider a very simple model. Everybody knows Nambu Yoshino Lagino model, NJL model, basically. And yeah, this kind of model. Then cover the structure transformation. P is a chiral symmetry breaking order parameter. Very simple. But as far as I understand, this is not integrable. So dynamical critical exponent is defined by, this is a wave function renormalization constant, velocity renormalization. So in non-relativist case, you need 2 renormalization constant, not 1. So these 2. So when V goes to 0, in this case, so dynamical critical exponent band diverging means that the velocity becomes 0. It means the band becomes flat. So all electrons are involved in this process. So equivalently, the physics shows the dimensional reduction from D dimension to 0 plus 1 dimension. And here I want to show spontaneous chiral symmetry breaking with the dynamical critical exponent diverges.
Sorry,
So
what is big D?
Big D is a space-time dimension.
Is now is what is for did you assume the any 4-dimension or D is big D is 4 or
So
something?
I will show the concrete result when D equal 2.
Okay, and
Yeah.
when you do a dimension reduction, do you ignore the KK mode?
Here I'm considering QFT, quantum field theory. You don't
Yeah,
have to consider. So yes, basically I will solve the ground state. So basically,
yeah. When you do dimension reduction, you have some Ki-Seok current mode.
so
but did you say
here I will not perform dimensional reduction by hand. So the original ground state is basically, this is the full D-dimensional system, but the ground state as an emergent solution shows 0 plus 1D like solution. That's the statement.
Okay.
So it emerges, not put in by hand. I do not. Yeah.
Okay.
Yeah. I want to derive this. Yeah, strong coupling solution. Yeah. Sorry for this busy slide, but basically this is everything. So I have 3 coupling function wave function renormalization constant, velocity renormalization, and four-Fermion interaction renormalization. So they evolve through emergent extra dimension. This is the algae flow equation. So just integrate out this Lagrange multiplier field. You have some algae flow equation for this one. This beta function is given by just derivative with respect to this value omega w pi w psi for this effective potential. So this effective potential appears from at given slice at given algae scale G. This is basically algae scale. At given energy slice algae scale G, we integrate out the matter field. At given scale, all this coupling function, order parameter, some chiral symmetry breaking order parameter at given energy scale defined as D, then we integrate out when this background field, this all becomes promoted to a background field. Then just integral. Then we have some effective potential at given as a function of this collective mode. Then derivative with respect to each collective mode, then we have beta function. Then this coupling function shows algae flow. So beta psi is derivative with respect to each Hubbard collective mode field. So I have 3 algae flow equation for each coupling function. Very clear structure, simple structure. Then with this renormalization, we have some energy dependent mean field equation for the chiral symmetry breaking field. This is the structure. So everything is determined by effective potential at a given energy scale in the background of renormalized coupling functions. Then derivative with respect to such collective field functions. I have some beta functions. And this full algae flow finally appears in IR boundary effective action. This is GF. So fully renormalized one appears in the final. So this is UV value. So everything is determined in this effective action. This algae scale, this part determines the algae flow of coupling functions, chiral symmetry breaking field, and fully renormalized coupling functions appear in this one. So with this one, IR boundary condition, UV boundary condition are determined in this effective field theory. So essential feature in this holographic dual effective field theory, holographic means I have some emergent extra dimension G in addition to D dimension. But later I will relate this into some metric tensor, gravity, blah, blah. So main feature is that field renormalization, velocity renormalization, and vortex renormalization are self-consistently introduced with an algae flow for the chiral symmetry breaking field at a given energy scale G. So in this respect, you regard this framework as some energy scale dependent mean field theory with self-consistent renormalizations in the large N limit. So in this effective potential at a given energy scale plays the central role. But this is very highly intertwined. Non-linearly coupled equations is impossible. So at the way how to solve this one is the same as usual holographic way. First, you consider some vacuum solution and introducing fluctuations around that. So I'm considering the vacuum solution first. So I introduce translational symmetry, which means that all x dependence I delete. All x dependence I delete. So now it becomes very simple. So field renormalization, vertex renormalization, velocity renormalization, and with effective potential, then translational symmetry is recovered. That's a vacuum solution. Usually we consider. Now you can calculate the effective potential. In this renormalized coupling functions, you can consider, then you have some, at given n scale, you have some just free partition function, free energy of the relativistic parameters. That's it. Then introducing this one, blah, blah, and derivative, finally, you have some full expression. So this is some RG flow equation for the chiral symmetry breaking field, and this renormalized functions are given by beta function. This is the beta function for W psi, field renormalization, velocity renormalization, vertex renormalization. This is the vacuum effective potential. Then, and all these renormalization constants appear in the IR boundary condition and boundary action. Then the remaining thing is just variation and solving the differential equation. That's it. But, I mean, the procedure itself is very straightforward. Nothing special here. Yeah. The only information is RG flow and some order parameter mean field theory are intertwined in a self-consistent way. So you can consider general dimension with this one, but yeah.
So your evaluation is analysis without any strong couple or weak couple.
Sorry, I cannot hear you, Chente. So will you repeat again?
I think your evaluation does not have any approximation for the common constant. Is it correct?
So I'm not saying this is exact. This is not exact, but I'm claiming this is non-perturbative, which means that if you, so it's not, that's an important issue, but it's not easy to explain. But basically, in the usual perturbation theory sense, if you consider large n limit and 1 over n, and it's just odd n to the 0 and 1 over n, 1 over n square. If you consider all over the resum, then you have some new n here, and with the new emergent RG direction. That's the structure. So all the model are resummed. All the model are resummed in a non-perturbative way.
Yeah.
So mean field theory with some RG are copied.
Yeah, I just find that you have some singularity when lambda chi goes to very large.
It's not. It depends on how to present it. If you integrate out this one, blah, blah, then just scale. Yeah.
I just saw when you go to the next page, then you will find that
you can see the solution. Yeah, they are all non-linearly intertwined. Yeah, it's not easy to. Yeah.
So when lambda chi goes to very, very large, you should see some singularity there. So in some
it's not. It's not. It's not. You will see. You will see.
Okay.
You will see. Yeah. So the RG flow equation. So variation of the previous effective action with respect to all the coupling functions and field, I obtained this equation. So this is an emergent extra dimension. Lambda is cut off, UV cut off. That equals 0 is UV. That equals lambda is IR. So x equals 0 is UV. X equals 1 is IR. So first order differential equation. This is standard conventional algebraic flows for all coupling functions. This is the second order differential equation for the chiral symmetry breaking field. Then UV boundary condition, which defines the theory at UV, and UV and IR boundary condition, which also can be derived from the effective action. But it's impossible to solve this one. Then from this part, Yoon-Seok solved everything. So he used the matching method. We have three first order differential equation and three UV boundary condition and one second order differential equation for chiral symmetry with both UV and IR boundary condition. We divide these differential equations in two subsystems. Four coupled nonlinear differential equation at UV and IR. Then in each region in this, they become simplified, but still nonlinear and highly intertwined. But yeah, near UV. Solutions of three first order differential equations are determined with three UV boundary conditions, so completely determined. And the solution of one second order differential equation, chiral symmetric field, is given by the UV boundary condition, but one unknown IR boundary condition. This should be determined by the matching method. Near IR. Also, in the same way, solutions of three first order differential equation are given by three unknown IR boundary condition. This should be determined. And second one, then this known IR boundary condition, unknown UV boundary condition. If we require matching, so between UV and IR solutions, so unknowns is this and this one, total 1, 2, 3, 4, 5. Matching at GW for field normalization and GV for velocity normalization, G lambda for each value, each RG scale. Because these are first order differential equation, we require two matching points. Then all these determine the two unknowns for each RG flow. Then this one for the chiral symmetry breaking field, this is determined. So this is second order differential equation. We need three matching condition. Then all three values are determined completely, UV and IR. You can find some analytic solution at IR. The detailed form is not important. Lambda, coupling function, field normalization, chiral symmetry breaking field, velocity normalization with some IR boundary values. We check out these analytic solutions are quite well matched and consistent with the actual differential equation in IR region. Also, you have a UV. Now so X is extra dimension G for this value. See, this is UV and IR well matched. Coupling function and field normalization. It iterates into some finite value, and UV and IR matched here. And also, velocity, interestingly, it vanishes. From finite value, it vanishes. You have some chiral symmetry breaking field value also. So let me summarize it. RG flow from a weakly coupled UV fixed point to a strongly coupled correlated IR fixed point. This is what we showed. So as a result, we found dynamical critical exponent infinite chiral symmetry broken state characterized by this finite particle weight of log So finite weight of local particle excitations with a gap. This is the result. So the question is this one. So phase diagram is like this one. Although this is somewhat speculative because we consider the zero temperature and algae flow. But I just translate. At high temperature, this is 1 plus 1D. There is no phase transition. Infinitesimal this one, you have some chiral symmetry breaking. Almost free perturbative UV CFT fixed point here, this one. You can call this ADS3. Zero temperature. Then we have some two crossover. One is spontaneous chiral symmetry breaking in the weekly. If you recall the algae flow, at first the velocity is still finite, but you have some chiral symmetry breaking solution. It's like a PCS, as discussed before. And finally, this velocity flows to zero. This is the result. This is the result. You may ask, what's the geometry interpretation? This is the final. So formally, you can introduce some. You introduce some geometric object. Put this effective field on a curved space-time background in a formal way. So Fierbein and this one. Then you apply algae in the same way. Then finally you obtain. So chiral symmetry breaking field, scalar field evolve, and this metric evolve in this way, and this coupling and effective potential is given by, again, at a given scale, you obtain just the integrate out. Then in the maybe based on Higgs kernel, whatever you like, you obtain some Einstein Hill protection, blah, 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 and beta function is given by this one. Sorry for fast, but derivation itself. But important point. So basically, you can compare this part and the previous part. The same thing. I just changed the Greek letter in a curved background. There are several terms, but yeah. Basically, if you compare this one, this can be identified with field renormalization constant. This can be identified with some velocity renormalization. And if you identify in this way, you can see this one. Then you may interpret this in a geometrical way. But basically, the resulting theory is Einstein's scalar type theory with an effective beta function. Of course, in this case, we didn't solve this one. So we couldn't show some emergent ADS2 or such kind of some dimensional reduction explicitly. But in the previous notation, we have, so from this one, is some crossover. So based on, we speculate this UV geometry is some, but yeah. So in higher dimension, maybe when the velocity is less than some critical value, then maybe if velocity is larger than critical value, we should have some conventional perturbative result. But in this case, some smaller value, some quite flat. So I speculate. So based on this kind of calculation, I speculate from some dimensional reduction, generically. So that's yeah, final result. Yeah, that's it.
Yeah.
Thank you very much.
Yeah.
Yeah. Any questions?
I think in high dimension, you need to introduce the kinetic term to the scalar field, because at least in the flat background, if you do not introduce the scalar kinetic term of the scalar field, this theory will not be renormalizable.
So the point is the strategy is, so first I'm considering vacuum solution. That's some X independent, so uniform configuration, so no kinetic energy. Then within that background, you may introduce some fluctuations. Then you have a second order differential equation, derivatives with respect to the extra dimension coordinate Z and X dependence. That gives, yes, you have some solution, fluctuation solution. But here, I'm considering only vacuum solution. Yes, yeah. In linearization, fluctuation, when you consider fluctuations, yes, you will have kinetic energy. Yeah, it's true.
Ki-Seok?
Yeah.
So are you saying that you start from chiral symmetry breaking parameter, maybe it is M here, right?
Yeah, M is phi.
So you
Yeah.
start from M equal 0,
Yes.
and
Yeah.
then finally in the IR you get non-zero.
Yes, right. So
So
this is the, yeah.
what gives you that scale?
So basically, what we found is that this IR value is given by some lambda some power less than 1. Less than 1. Lambda is UV cutoff and very small coefficient. This should depend on lambda chi some weight. So with 2 value, but we don't know. So let's see the analytic expression. Sorry, I didn't check out. So this is the final expression. So this is self-consistently determined IR bound. So this is the analytic expression. So yeah, this is the form. Sorry, I cannot satisfactorily answer that question, but lambda f and phi f all are determined this in a self-consistent way. Yeah, this is what I can say.
So
Sorry
you-
for, yeah.
Maybe you can express M in terms of this WF and lambda F?
This is M. Yeah, this is M. This is mass M. Yeah, this is mass M. I just change it, phi to M. Chiral condensate. This is in perturbative sense, chiral condensate.
So that is I mean what I was asking. You didn't give background geometry at first, right?
Here, geometry means that the renormalization constant is W and velocity renormalization this one. Yes, it's flat. At first, I started flat. Yes, no renormalization. And this is basically corresponding to phi by E tau. This corresponding to EX. Yeah.
Then maybe you may define, I guess, Vierbein and therefore
Yes.
metric, right?
Yes, right. Sorry for
Using from your
yeah,
results.
yeah. Next part I showed too fast due to some time limit. Yes. So this is wave function field renormalization is proportional to this part. Just comparison, just naive comparison. I didn't, yeah, take this somewhat seriously. Yeah. Yes, you are right. You can read off, but you can solve this differential. I mean, in this framework directly. Yeah, this framework directly you can solve. You can compare directly, but this is complicated. We couldn't. But just yeah, this comparison you can check out. Yes, you can read off.
Basically, your scale is coming from the integration constant. Can you see the expression of phi again, which is very complicated one?
Me too. So yeah,
Yes, here.
So
WF and the lambda F.
They are all determined self-consistently from the matching method. So and with the boundary condition. So there are all are determined by UV value. Yeah, this one and some boundary condition bound Z P 0 and so this is defines the UV theory itself. with the cutoff lambda. Yes.
Yeah, it's quite amazing that you can solve such a thing.
Yeah, he,
Yes.
he, not me. Yeah, yeah. So there is some trick, but he showed this approximate solution is to fit the differential equation solution and numerical solution. I mean, in each region, UV region, IR region. So I believe this solution is trustable. The only problem is just derivation, beta function. Yeah. With that assumption, yeah, this is the solution in 1+1D. Unfortunately, I can check out some numerical result. I tried to find review some papers. I couldn't.
I see. This is
Yeah.
I mean the fit of the numerical data, you say.
No, this is the analytic. He solved the way in
I see.
an approximate way, but he checked out this solution fit the numerical result quite well. So this is confirmed. So what I want to say is, this solution is confirmed. So
Okay.
yeah,
Are
sorry
there
for
any
yeah.
yeah,
More
no,
questions? Yeah.
are there any further questions? So if not, let's thank speaker again for a very interesting talk.
Thank you very much.